Hi guys, so I will briefly go through how the circuit works first before going in depth, stage by stage. So first, the microphone picks up the heartbeat sound from a stethoscope's acoustic output. The mic has a weak audio signal, which the preamp would amplify and boost to a level suitable for further processing. The preamp supplies a voltage gain of somewhere between 10 millivolts to 1 volt. The preamp is then connected to a low-pass filter which removes the high-frequency noise. Then, it is connected to the audio amplifier which amplifies the filtered signal to drive a speaker of 0.5 watts and 8 ohms. The speaker is then able to broadcast the hard sound. In the first stage, the signal passes through C1, a coupling capacitor, which blocks off any DC signal, only allowing AC signals to pass through. At TP1, there is a voltage divider circuit which gives me an output voltage of 4.5. How I got 4.5 volts was I took 10k over 10k plus 10k, everything times 9 volts, and that's how I got 4.5 volts. This voltage divider circuit is to ensure that the input voltage for the op amp isn't 0 volts. Without the voltage divider circuit, my output would be distorted as it would be clipped off. With the voltage divider circuit, it shifts the voltage to 4.5 volts, ensuring minimal to no distortion in my output. Before moving on, let me provide you with some info on this IC. The TL072 IC is a low-noise JFET input op-amp which is ideal for bios signals. As you can see here, R2 and C2 form an active low-pass filter which helps me to determine the upper critical frequency. I derived the cutoff frequency of the low-pass filter by using this formula, 1 over 2 pi R2 C2, which got me 1.064 kHz. R3 and C3 form an active high-pass filter which helps me to determine the lower critical frequency. I derived the cutoff frequency of the high-pass filter by using this formula, 1 over 2 pi R3C3, which got me 15.915 Hz. As you can see, both of these low-pass and high-pass filters form a band-pass filter, which only allows a specific range of frequencies to pass through while rejecting all other frequencies outside this range. Before moving on to the next stage, it passes through C4, another coupling capacitor, to block off DC signals to only allow AC signals to pass through. For the first stage, the power supply is set to 9 volts while the function gen is set to 200 Hz and 200 mV peak to peak while being at the high C setting. It is connected to C1 and ground while the oscilloscope probes are connected to the points TP1, my yellow waveform, and TP2, my purple waveform, while also being grounded. Here you can see that my TP1 is around 200 mV while my TP2 is around 4.8 volts. Here I measured the same stage but with a 1 kHz frequency instead, resulting in my TP1 to still be around 200 mV, my TP2 is around 3.4 volts. Here I've recorded the gain for both measurements, and as you can see, with the higher frequency, the lower the gain. This is because of the low pass filter which allows lower frequencies like 200 Hz to pass through, while also reducing the higher frequencies like 1 kHz. For the second stage, R4 and P1 are used to calculate the gain. The formula for the gain is minus R4 over P1. This value can then be adjusted by adjusting the potentiometer by twisting it. R9 and R10 once again form a voltage divider circuit for biasing, like the previous voltage divider circuit in stage 1. Using the same formula, I got an input voltage of 4.5 volts. This is also an inverting amplifier, so you'll see later on that my TP3 waveform will be out of phase from my TP2. The power supply is set to 9 volts while the function gen is set to 200 Hz and 200 mV peak to peak while being at the high Z setting. It is connected to C1 and ground while the oscilloscope probes are connected to points TP2, the yellow waveform, and TP3, the purple waveform, while also being grounded. As you can see, TP3 is distorted at first, however, after adjusting the potentiometer, the waveform slowly formed a sine wave. This results in my TP3 to be around 5.64 volts right before distortion, while my TP2 is 4.48 volts. As I said, my TP3 wave is also out of phase from my TP2 wave due to the inverting amplifier. So how does a potentiometer work? A potentiometer is a variable resistor, meaning that the resistance can be adjusted by twisting it. Since it varies the resistance, it also alters the voltage and current of the circuit. This is because of Ohm's law. So, when I decrease the resistance, the voltage increases. When I increase the resistance, the voltage decreases. For the third stage, the signal passes through C5 first, another coupling capacitor, which blocks off DC signal, only allowing AC signal to pass through. Once again, there is another voltage divider circuit which provides a DC offset voltage of 4.5 volts. Next, you can see that there is a salient key second order low pass filter because of the pair of low pass filters. R7 and C7 form a low pass filter, while R5 and C6 form another low pass filter. C7 provides feedback for shaping the response near the edge of the pass band. These low-pass filters control the cutoff frequency, which can be calculated by this formula: 1 over 2 pi times the square root of R7 times R5 times C7 times C6, which is 1.023 kHz. Finally, the coupling capacitor C8 filters the signal, blocking off any DC signal while only allowing AC signal to pass through. The power supply is set to 9 volts while the function gen is set to 200 Hz and 200 mV peak to peak while being at a high Z setting. It is connected to C1 and ground while the oscilloscope probes are connected to the points TP3, the yellow waveform, and TP4, the purple waveform, while also being grounded. Here you can see that both my TP3 and TP4 are around 5.68 volts. Here I measured the same stage but with a 1 kHz frequency. My TP3 was around 4.24 volts and my TP4 was around 2.2 volts. At 200 Hz, you saw that my TP3 and TP4 are equal. This is because there were no feedback resistors, which usually provide the gain for this circuit. Hence, I achieved unity gain, which means that our gain is 1. At 1 kHz, you saw that my TP4 had decreased drastically, which meant that my gain also decreased. This is because of the two low-pass filters which had affected my output. Because of the negative 40 dB per decade roll-off rate, the voltage can attenuate sharply at higher frequencies, especially at frequencies higher than the cut-off frequency. In stage 4, the signal enters the trimmer through pin E and exits through pin S. Similar to the potentiometer, the trimmer is used to adjust the voltage amplitude before reaching the amplifier. In other words, I can adjust the volume by twisting it. Pins 2 and 4 are grounded to set a 0-volt reference for my input signal and enable a single-ended input operation. C15 and R17 form a Zobel network which helps to stabilize the impedance at high frequencies. It also prevents high-frequency oscillations and improves frequency response. This network is usually found in audio amplifiers, especially in power amplifiers like this LM3864 IC. This network is connected in parallel to the speaker to minimize the effects of the inductance already present in the speaker. The very last capacitor, C13, is a coupling capacitor blocking off DC signals and allowing AC signals to be amplified at the speaker. The power supply is set to 9 volts while the function gen is set to 200 Hz and 200 mV peak to peak while being at a high Z setting. It is connected to C1 and ground while the oscilloscope probes are connected to points TP4, my yellow waveform, and TP5, my purple waveform, while also being grounded. Here you can see that my TP4 is around 5.52 volts while my TP5 is around 6.88 volts. Here, I measured the same stage but with a 1 kHz frequency instead. You can see that my TP4 is around 2 volts while my TP5 is around 2.72 volts. I didn't record my waveforms for this, but a huge mistake I made when I was doing my measurements was that I constantly moved the function gen for every stage I measured. So at first, I didn't know that the function gen was supposed to stay at C1 the whole time. So I kept on moving it to the next test point as I kept on testing each stage. And then I wonder why my waveform looked a bit funny. But then after consulting with my friends, I realized my mistake and I corrected it. And after correcting it, I immediately got the results I wanted. So my takeaway here is that I should check thoroughly because even though my connections were all correct, a simple careless mistake could affect my results really drastically.